but at the end of this semester. No, at the end of this week. So this is going to be my last day with you guys. Didn't know about this until break. You sent me the email. I'm sorry, I did not. I've been dashing, and I meant to return it, but Tony's going to take over. Tony Crossland. So, so Tony's going to take over, and therefore you can direct all your questions at Tony. Let me see. We've gone up through sectional in here. This stuff with spring break and everything makes everything tough. So we are sitting in 14.3, which I did part of, but not very much. I didn't work out very many examples, and I didn't work out certain types of problems. So I'll finish that up today. And I'll probably just let you do 14.4 on. And then as far as tests go, do you want?
I would probably recommend you give them a test on up to where you stop tonight.
Okay.
If possible.
Yeah.
How many tests did you, I should have asked you this before class. How many tests did you have planned for the whole semester already?
I think I said 4.
4 total?
But you realize 2 weeks we lost.
Right, you were decimated by the Tuesday, Thursday, Saturday, so.
So, I don't know exactly. If I thought that they were going to do something like get rid of finals week and treat that as a regular week, but I guess not.
Were you doing a comprehensive final exam?
I always do, but I had I not had a leave, in the back of my head I was thinking about not doing the comprehensive because the last batch of stuff.
Yeah, sometimes you can do the final exam slot as like the last test.
Yeah,
as opposed to,
and so that's kind of what I was thinking. So what that means is, when would you want to test?
Do you use the entire 2-hour time block for
I
a test?
have.
Okay, so a week from tonight, maybe this time next week, next Tuesday.
Okay. I personally would have. I tend to try and do tests on Thursdays.
Okay.
Only because that gives people the weekend, and then I can go over questions on Tuesday.
We can do that if that's the what you've done for test 1 so far. So
26th.
So that would be next Thursday. Okay.
If that's all right.
Yeah, that's
Is
fine.
there the possibility of putting it in the testing center since we've already lost so many class hours?
That was going to be the other thing I was going to suggest, and this would prevent you from losing the 2 class days. And if you did that, Tuesday, Wednesday's usually the
That's
best.
their best days.
Yeah.
How many of you would be able to do a Tuesday, Wednesday testing center test?
What time is the test?
The testing center opens at, I think, 8:30 or 9 on Tuesdays and Wednesdays. And they close at 7:30. So I know the trouble with evening students is usually accommodating a work schedule and things like that. So those are the most robust hours for the testing center during the week is on Tuesdays or Wednesdays. So if any of you could, I could offer it in the Beth could offer it in the testing center.
Well, I won't
We could
be
offer it
here.
in the testing center.
Yeah.
So you have a plurality of teachers at home.
Normally what I would do is say, if you can't make it, make sure you, see Tony.
Yeah, we'll iron out the details, and I'll make sure you're aware of what's going to happen on Tuesday, Thursday night this week.
Okay. And somebody said D2L that was that for this?
I think they've added me as the teacher now, so
I
can
don't know
start
if I
posting
still
things.
have access.
Oh.
I don't know, so I'll need to do a study guide.
If you don't have access, you can email it to me and I can post it.
Okay. So, all right. So let's get covered what we need to. All I did with partial derivatives was compute a few of them. And there's a lot of material that's left to handle in this section. So, given the homework problems that I suggested that you could start doing, do you have questions over them? These are the computational ones. Yes, no? Is this okay? Okay. All right, so let me remind you of notation. So, well, actually, if I have a function and that function is of two different variables, then I can talk about the partial derivative with respect to one of those variables, so partial of f with respect, in this case, 2x, and this basically is going to mean to hold y constant and measure the rate of change of f with respect to, so WRT, I think I abbreviated for you guys before, with respect to x. And that's what this is representing. It's called a partial derivative. The other notation for it that you will see is f sub x. This notation, the df dx, with the d's kind of curled back, the advantage to this notation is it makes it very easy to chase down units. So if, for instance, I look at P being pressure of a gas, ideal gas, and that's a function of the gas's volume and temperature, then when I look at the partial of P with respect to, say, temperature, if I'm telling you that P is pressure and its units are atmospheres, if V is volume, its units say liters, and T is temperature, Kelvin units, then when I go to figure out what the units of the partial of P with respect to T would be, it's going to carry the P units in the top, so this is going to be atmospheres per Kelvin. So it's basically coming from that, the same old difference quotient stuff that you did in Calc 1. Okay? It's understood in this context that T is being held constant. If I look at the partial of P with respect to V, then the units here are going to be P units, atmospheres per liter, the volume units. Okay? If I have a function g, which is a function of 3 variables, well, I can take partials with respect to x, y, or z. It all amounts to the same thing. Okay? So, you guys okay computing these? Do I need to work an example or two? Please? Okay. So, we'll see as we work out some other stuff how easily these things come. One of the things that we need to look at are second derivatives. And this is where it starts to get slightly more complicated than Calc 1 type of derivatives. And that's because if I start off differentiating with respect to x, that's a first derivative. But when I look for a second derivative, I can differentiate with respect to x again, or with respect to y. So, the notation we use for second derivatives is going to be very similar to the notation that we use for a function of one variable. So in Calc 1, we call this f double prime of x, or we could use that D notation, and typically they'll put a 2 up there in parentheses so it doesn't look like a square. The key on this notation, which admittedly looks weird, is if you can keep the notation straight, it gives you a fighting chance to figure out units easily. So if, for instance, F was measuring concentration in milligrams per liter of some chemical solution at a particular time, which say we're measuring it at seconds, then the units here, as long as you keep in mind this square is on the D, you're going to pick up units of F, which are milligrams per liter divided by the square on the unit of X. So in this case, I guess I should have had a T here, but seconds squared. So in other words, you're picking up the numerator units divided by the square of the denominator units. And the notation looks weird the first time you see it, but that's why it's the way it is. That's what's actually happening there. And it's the same deal here with these second derivatives. So if I look at something as simple as the ideal gas law, it would look like this. Okay, so K here is positive constant. And if I keep the same units that I indicated up above with pressure, atmosphere, and temperature, if I go to measure the rate of change of the pressure with respect to volume, so compute the derivative and write down its units, and then repeat with partial of P with respect to T. So differentiate each one of those and write down associated units. Okay, so with each of these instances, when you go to take the partial of P with respect to V, I'm thinking about pressure as basically being a constant multiplied by V to the minus 1. And so this derivative is going to be minus KT V to the minus 2, or I'll just divide by V squared. As far as units go, I'm going to have pressure units in the top, atmospheres, and volume units in the bottom, liters. In this case, if you go to take pressure with respect to temperature, you're going to treat, well, K is always a constant here, but here you start treating volume as a constant. And so the only thing you go to differentiate is T, and that derivative is 1, so you're just left here with K divided by V. Units here are going to be pressure units divided by temperature units. Atmospheres per Kelvin. The constant of proportionality up here contains units. And what those units are going to do is take the units of, in this case, Kelvin divided by liters, and the units of K, which involves the amount of gas and then that gas constant, it's going to convert those units over to pressure units. There's also numerical constant in there. I mean, it's numerical in value. You guys see this? Okay. Now, as far as second derivatives go, this is a function of two variables. I can differentiate twice with respect to V. So we have the first derivative with respect to V, and I differentiate this again. The minus KT, that's just another constant, so it's just the 1 over V squared that I go to differentiate. That's going to bring down a minus 2, and then drop the power from V to the minus 2 to V to the minus 3. So I end up with this. Is this okay? You guys seeing where this is coming from? You guys are quiet tonight. It's because of timing.
Am I
Where did
weirding you out? I'm sorry. I was still trying to be invisible back here.
Where'd you get the 2 from? I wasn't looking.
I don't know where I got the 2 from. I didn't.
You're ahead of
There, you're wrong. There's no 2 there now.
Makes sense.
There should be. You're coming from V squared, or basically V to the negative 2.
Oh yeah, there is a 2 there. See? Okay. I'm differentiating this guy.
Oh, so you're bringing it up.
Yeah, so I'm just thinking of this as minus KT V to the minus 2.
Okay.
So I bring down the minus 2 and then drop the power by 1. Okay? I'm going to come back up and do units in a minute. Second derivative of pressure with respect to temperature. There is the first derivative. This derivative, 0, because this is being seen as a constant. There's no variation. P isn't going to vary, or the first derivative of P with respect to temperature is not going to vary with temperature. There's no temperature there to have it cause any effect. All right? Now, as far as units go, you're going to do this in the same way that you figure units out for second derivatives in Calc 1. So I'm going to put P units, atmospheres, and then square of my volume units. Here, second derivative of pressure with respect to temperature, I'm going to do atmospheres up on top, and then square Kelvin units. See how it goes here. Okay, now, this guy is possibly a bit of an issue. It's a second derivative. I'm going to be differentiating with respect to V and then differentiating with respect to T, unless this means differentiate with respect to T and then with respect to V. The question is going to be, is there a difference? And thankfully, the answer is no. Okay? As long as you have reasonable behavior of these functions and their derivatives, reasonable functions and derivatives, nice and continuous, you know, as long as you stay away from trouble spots, it does not matter the order in which you differentiate. You will get the same answer either way. So, for instance, I could start with this, the partial of P with respect to V, and then differentiate it with respect to T. So, I would take the partial derivative with respect to T of this derivative minus KT over V squared. You differentiate here. T is the variable. The minus K over V squared is a constant. I just end up with this. Or you could have differentiated first with respect to V in, did I do this right? No, differentiated first with respect to T, and then with respect to V, that's a V there. Okay, so I'm just using my above first derivatives to put in here. And notice that if you differentiate this, this is the same thing as looking at K over V as KV to the minus 1. Drop the power down by 1. You get minus K over V squared, exact same answer. Meaning you don't have to worry about X's, Y's, what's the order, T's, V's, what do I do first here? Okay. Which gives rise to standard problems such as the following. Let's see. So suppose you're asked at this point to find this partial. You can differentiate in either order. So what's the order? What's the first derivative you want to do?
Tan of xy.
With respect to,
X.
why not y first?
Does it matter?
Yeah, it's gonna matter.
Okay.
It doesn't matter.
Well, yeah, I guess y because there's everything else is with.
Yeah, look at the mess over here.
Yeah, makes sense.
You want to look at these problems. I've put problems like this on exams after I've shown this in class. You don't want to differentiate this. It's a mess. So if you begin by taking the partial of f with respect to x, that whole thing goes away. So what are you going to get? The derivative of tangent of some stuff is secant squared of that stuff. And then the derivative of this, of the xy, with respect to x, we're treating y as a constant. It's going to pull y out front. And then differentiate with respect to y. It's a bit of a pain in the neck here. It's going to be product rule. So we're going to end up differentiating the y, leaving the secant squared alone. Add. Leave the y alone. This is going to be a bit messy, but you're differentiating secant the quantity squared. That's going to be 2 secant of xy times the derivative of secant of xy. So that's going to be another secant of xy. I don't know why I chose secant here, or why I chose tangent. Tangent of xy. And then to differentiate xy with respect to y, we're going to have an x. So let me make sure I've done this right, and I'm differentiating for this part here secant of xy squared. So the y here is coming from keeping that factor, okay, it stays put. I'm differentiating secant the quantity squared. That's going to give me 2 times the secant. And then I'm differentiating with respect to x, my secant of xy. Derivative of secant is secant tangent. And then this x right here is going to come from differentiating with respect to y, that product xy. Big, messy, product rule. Just messy. Regardless of how messy that is, it's nothing compared to what this would be. Okay? So you want to kind of scan through these derivatives if they're higher order. The one thing I forgot to mention over here is units. Again, P units, that would be atmospheres on the top per liter Kelvin. And those would be the units for either one of these. Okay? Questions? Okay. Numerical data. So this bugs me in this book, but they're not giving units on this, which drives me nuts. But they're looking at seawater density as a function of two variables. One variable is temperature, the other variable is salinity. And so you did problems similar to this in Calc 1 where you estimate derivatives. And that's what I want to do with this. We're going to estimate partial derivatives, and they literally will give you a nice feel for what these partial derivatives are actually doing. So, suppose I want to find the partial derivative of the seawater density with respect to changes in the temperature. And I'm going to do this, let me see, let me put these numbers in order, T and S. So I want to do this, let's say, at the point 832. So the best I'm going to be able to do here is to come up with an estimate. Okay. So if I look for 832, it's 24.93. That's the density at that point. If I want this estimate, temperature is what is varying, but the salinity here, that's constant. So the numbers I would look at here, am I right in your book, Tony, with pencil?
Yeah, that's fine.
Okay. So we're looking at, let's see, 832. We're looking at this block of stuff, but I'm going to hold the salinity constant and vary temperature, so I'm going to be reading up and down like this. So what I would do would be to estimate this using a difference quotient of
Pull the paper a little bit.